Okay, let's go to chapter 19, which is the first law of thermodynamics. The first law of thermodynamics is just conservation of energy. Let's define first thermodynamics. Thermodynamics, right, treats the transformation of heat into mechanical work and the conversion of work into heat. Okay, also let's define a new quantity in thermodynamics. Correct. Let's define the internal energy. The internal energy is just the sum of all the energies on the system, like translational kinetic energy, rotational kinetic energy, potential energy, and vibrational energy. Okay, perfect. That should be the internal energy. One example of that is this. Imagine that we have these two containers with 2 liters of water, and one is at 80 Celsius and the other one is at 100 Celsius. Okay, according to this definition, of course, because it's hotter, it has more rotational energy, right, than this one. So this amount of water can do more work, let's say, in melting this ice. It melts more ice, right, than in this case because it has more internal energy, because it's hotter. Now, what happens if they have the same temperature, let's say 80 and 80? Well, if they have the same temperature, 80 and 80, well, they melt the same amount of ice. But what happens if this one has more water, let's say 6 liters? This one has more water, even though they have the same temperature. This container has more internal energy and it can make more work on melting ice than the previous one. See how we can relate the internal energy? Also, remember in the previous chapter, we found that the translational kinetic energy, correct, for a monatomic gas. Now let's go back to gases. Okay, is equals to 3/2, right, and RT. Perfect. For ideal gas, again, the total energy is just the translational kinetic energy. When we go back to the definition of internal energy, which is the sum of the energies, and we take again the case for monatomic as well, it's found that the internal energy is equals to the translational kinetic energy. But translational kinetic energy is equals to 3/2 nRT, so we can define then that the internal energy for monatomic ideal gas is equals to 3/2 nRT. Actually, the most important quantity is not the internal energy, but the changing internal energy, right? The changing internal energy equals to 3/2 nR delta T. So we have a new quantity in thermodynamics, okay, which is the internal energy. And the internal energy, one more time, is equals to 3/2. This is for monatomic gas. For diatomic gas is a little bit different. We change only this factor. We're gonna see it later. Perfect. Gonna be nRT then. The changing internal energy equals to 3/2, correct? nR delta T. Perfect. Actually, this is one way how we define the internal energy. The internal energy is defined as 3/2 nR RT. That's the definition of internal energy. Okay, this is for monatomic gas. For the atomic, it's a little bit different, but again, we define it like that. Perfect. Now, let's see what happens when we're dealing with processes, correct? Let's relate thermodynamics, right? When we have a system, we put some heat, we go to a new system, right? Put some heat or do some work, we go to another system or state. There is the same system but different condition, right? We call this, when the system is in equilibrium, we call this state, which is specified using, right, the state variable. So we have again these 2 types of variables. We have transfer variables, and we have state, right, variables. For transfer variable, we have work, and heat. And for state variables, we have pressure, we have volume, we have temperature. Now we have a new quantity, the internal energy. Also, we have a mole, which is the numbers of moles. Okay, these are again the state variables. These tell us the state. It's, for example, when we're dealing in kinematics, mechanics, right? Kinematics, we determine, right, or describe motion of the particle once we know the position and velocity of the particle at any time. Imagine we have a particle, right, moving in this direction. Okay, what should be how we describe the motion of the particle at this time? Well, once we know what position 1, velocity 1. In another time at t2, right? How we describe motion of the particle, only one particle, right? At t2. Well, we need to know the position and velocity at that point, correct? The same thing happens when we have thermodynamic system. We have bunch of molecules, right? Right now, how we determine the motion, right? The state of the particle, the system, in this case. Well, similarly to this case in kinematics, correct? So we have a system right here, a system, and this system is established by the state variables, right? Which is what? P, V, T, and internal energy, correct? And this system must be in equilibrium. Okay, equilibrium, perfect. And we call this state 1, for example, like right here, position 1. Okay, the state 1. Now, right here, what are the interaction for particles? Interactions are just forces. Forces are collisions, right? Collision. These are the interaction. Right here, what is the interaction between two a state of a system, right? Now let's go to another state. Like over here, another position, over here, another state. The interactions are just the transfer variables, right? We use the transfer variables, which is heat or work, to go from one state to another state, correct? So in this case, state 2. Perfect. Again, to specify this state must be in equilibrium. When the state is in equilibrium, we can determine the pressure, volume, temperature, and internal energy of that system. Now let's go to another position for one particle. Now we have a system. Okay, the same thing. We have to work with heat and work, right, to get to the new state. A new state. Now it's gonna be state 3. Again, must be equilibrium with new pressure, volume, temperature, and internal energy. Got the idea? Okay, perfect. Now, taking this into account, let's go to a sign convention for these transfer variables. Okay, let's do it this way. Some books changes, right? Especially the convention, especially for work. But in this book, right, this convention is used. Let's do it. Imagine that we have a system, right? This is the system. This is the environment or the surroundings. Okay, if we add heat to the system, it's our system. This is ideal gas usually. Okay, when that happens, so heat is positive. If we are removing heat from the system, system is releasing heat, right? So in this case, heat is negative. Now, if the system does work on the environment, right? So work is positive. If the environment is doing work on the system, that work is negative. Correct? So this is the convention for work and heat acting on a system, thermodynamic system. Correct? Perfect. Now, let's see when we're dealing again with work. How do we define work? Well, work, as we know, is equals 2 force times change in x, for example. Okay, let's apply this definition to a system that is made of a piston. Currently we have gas right here, gas, ideal gas, and this system is doing work on the environment. So we have motion from here to there, correct? So we have the displacement delta x. Also we have an area. Remember it's a circular piston, so we have the area right there. So the gas, because we use some heat maybe, we change the temperature, so it's doing work on the environment. Correct? Perfect. So the work is gonna be positive according to this convention. Great. Now let's do it. So, but we have interaction with molecules. Remember, we found in the previous chapter, right? Forces is related to pressure, and we found pressure, right? And we determine in that case, right, energy in relation to the temperature. Okay, let's continue. Pressure is defined as force divided by area, right? From here we have that force is equals to pressure times the area. When we substitute this by right here, we get that work is equals to pressure area, right, delta x. Correct? Now what is this? This is just change in volume, right? Change in volume is equals to area change in x. Correct? So we can define then work, in this case, right, work is equals to pressure, correct, times change in volume. When the volume is this change is infinitesimal change, we can represent, right, this quantity in this way, pressure, right, dV. The change in work, right, or the work done by a infinitesimal change in volume, correct? And well, we represent this system, right, in a PV diagram, correct? Remember, we found before the Boyle's law. The Boyle's law says that when temperature is constant, T equals to constant, correct? We found that PV1 is equals to PV2, correct? This is Boyle's law from the previous chapter. Okay, and this is very important law in this case because this has the units of work, right? The units of energy, right? Units of energy, correct? So this is very important in diagram because we're dealing with energy. Remember, energy must be conserved. Okay, great. Now the isotherm, right? Going from 0.1, let's say, and 0.2. Okay, is represented in that way. That's the isotherm. This T equals constant. We found it before. Remember? Perfect. Now let's find the work done in this case. What should be the work done? Well, the work done is gonna be the area under the curve. Imagine that we have expansion going in that way. We have expansion, the work is positive, correct? And how do we define work one more time? Imagine this is the case. Okay, let's do it. So work is equals to, let's use this part, correct? The integral pressure dV from V1 to V2, correct? But this pressure is not constant. You can see in this isotherm, pressure changes, right? The same thing as volume. How are these two quantities related? Well, because we're dealing with ideal gas, we go to the ideal gas law, which says that PV is equals to ART, correct? And from here, we can solve for P, pressure, and what do we have? This is the integral from V1 to V2 of N RT over volume. In this case, one more time, the temperature is constant, okay, dV. When we do the integral, what do we have? This is equals to nRT, correct, ln of V2 over V1. Perfect. It is the work done by a system using T constant. We call this isothermal process, for example. Okay, perfect. Now, but look from here, using the Boyle's law, we can see that B2 over B1 is equals to B2 or P1 over P2. So we can say also that work is equals to nRT at T constant times ln of P1 over P2. Correct? Okay, so we have the work done in at constant temperature, correct? So now the nRT ln, correct? B2 over B1. Or we can use pressure. Remember, it's gonna be absolute pressure, right? Absolute temperature, and so on, because we're dealing with ideal gases. Okay, great. Now, taking this into account, let's go to. Let's go back to this one. Look, when we're going this way, expansion, we have expansion, the work done by the system is positive. When we have compression, now the work done on the system is gonna be negative. Correct? Again, this is the work. The work's gonna be the area under the curve, right? This is area is equals to work. But in this case, work is positive because we have expansion. When we have compression, it's gonna be negative, correct, according to the convention. Okay, perfect. Now, taking this into account, let's go to the first law of thermodynamics. Let's do it. Let's do it. Let's do it. So imagine one more time. This is a V2, correct? This is V1. One more time. This is a system, correct, with some pressure right here. And we have some volume, right? Some pressure, some temperature right here. Now let's add some heat to this system. When we put some heat, right? Heat is added. Correct, we are doing work usually, right? Imagine some movable piston, okay? So we have some delta X right here. Perfect. Now, in this case, if we use conservation of energy, it means what? Heat is converted into work, but also we have change in internal energy, right? We have a function, well, you can use change in before that, we have a change in temperature, correct? Plus work. That's what happens when we add heat to the system. Usually we have a change in temperature, right? Or in this case, if the piston is movable, we have work too. Okay, great. But look, the unit for temperature is not the same as for heat and work. So actually, this must be a function, right, that depends on temperature. What is that function that depends on temperature only? Is gonna be the internal energy, correct? So what do we have then right here? Instead of this, we use that change in internal energy. So heat is just converted into changing internal energy plus the work done by this system. And this is called the Phys law of thermodynamics. Okay, Phys law of thermodynamics. Also, we represent the Phys law of thermodynamics using the change in internal energy is equals to heat minus work. Well, these two are the same. So this is again the first law of thermodynamics. It's just the conservation of energy. Okay, perfect. I can't believe it. Okay, also, look, we can represent this using infinitesimal changes. Okay, infinitesimal change equals to heat minus P dV. Right, for infinitesimal changes. And what is the change in energy to? Well, we represent in this way for monatomic gases, it's 3 halves. For diatomic, it's gonna be like 5 halves, right, and so on. Perfect. I can't believe it. Yes. Okay. So let me see what else do we have for this chapter. We defined we're done, correct? We have expansion. Now let's go to an example that's given in your book. It says, let's go back to the PV diagram. It's a very important diagram, right? PV diagram. Or PV plane, correct? This is very important because we're dealing with energy. This is pressure, this is volume. Imagine that we have one state right here and we're going to know the state right here. How we can go from state 1 to state 2? Well, depends on the process, right? We can use isothermal process like that, or we can go using constant pressure and then constant volume, correct? Using, let's say, part A, or you can go, correct, using constant volume at the beginning and then constant pressure using, let's say, path B, correct? But at the end, look, at the end, when we're dealing with the state, again, we have state 1 and state 2, correct? This is state 1, state 2. Remember, we use heat and work to go from here to there. Great. The state doesn't depend on the path, right? Like a rate from here to here, from here to here. Depends only what initial and final position. If a function that depends on initial and final position only, right, is present, we call this quantity state of function, right? Or yeah, state of function, correct? Like for example, what should be the state of function for this case? Well, the internal energy, the change in internal energy doesn't depend on the path, depends only on the initial and final position, correct? The same thing for the other quantities, all states, correct? Like when we have potential energy, gravitational potential energy, remember? The change doesn't depend on the path, depends only on the initial and final position. The same thing happens right here, right? For internal energy, the change doesn't depend on the path, could be in this way, or in this way, or in this way, or in this way, correct? The change is the same, depends only on what? Initial and final position. That's for internal energy. Great. Now let's see what happens to work. Okay, so remember, we have different processes, correct? Imagine that we use the isothermal case, correct, from here to here. We found already, right, this is the work done, correct? What about if we use path A? Well, we use path A, right? It goes from here to here, right, or from here to here, correct? What should be the area under the curve, right? This is the area under the curve. This is work. Work. Okay, this is work. What about if we take the path B? Well, for path B, correct, it's gonna be in this way and this way. What should be the work done? This is the work done. Right? As you can see, work, right, depends on the path. You go to this path, you have this amount of work. This path, this amount of work. This path, this amount of work. So depends on the path, correct? The same thing happens to heat. Heat depends on the path. Why? Well, because look, how do we define internal energy? Internal energy, okay, the change in internal energy through A is equals to what? According to this law, is equals to heat, right, minus work, correct? Now the same thing happens to the change in internal energy through B, right? Equals to heat minus work. But look, we found that the change in internal energy doesn't depend on the path, right? It depends on the initial and final position. So the change from here to here is the same as the change from here to here. So these two are the same. But look, the work is not the same. The work depends on the path. If the work depends on the path, these two are the same, so heat also depends on the path, right? From this case, we found that work through A is not the same as the work, right, through B. Again, this is A and this is B. Or the same thing for heat, right? A and B path. If these two are not the same according to this analysis, right, these two are not the same either. So what is the conclusion? That heat through A is not the same as heat through B. So again, these are not variables of state, right? Because those depends on the path, correct? Depends on the path. But internal energy, the changing internal energy doesn't depend on the path, depends on the initial and final position. Look, in your book, we have this notation too. We have, I just found this, this representation in your book that I want to explain it because this is very, very important to analyze it. Correct? I found this equation, right? This equation 19.6, and it says that the change in internal energy is equals to change in heat minus change in work. Look, this is very important equation, correct? This is a state of function. When the state is when the quantity is a state of function, the integral, right, of this u, right, is gonna be final minus initial. But it doesn't happen. It doesn't happen to heat and work, right? Heat, if we integrate heat like we did for internal energy, this is not the same as final minus initial. It's not the same. Why? Because this is not a state function. This depends on the initial and final, right? Initial and final. But this one, right, depends on the path. Correct? The same thing for work, right? If we integrate work in the traditional way, right, this should be equals to what? Final minus initial. Correct? Final minus initial. But one more time, right? This is initial and final position, right? We take different path, right? The words are different. So this is not exact integral, right? As it is for the internal energy. Internal energy is correct. In some books we use this notation. Right? That notation to specify that these are not a state of function, but the internal energy. Correct? So be careful with that. Now let's go to the case when we have a cyclic process. Okay, when we have a cyclic process, like in this case, again, PV diagram, we have state 1, state 2, and let's take these two paths. Let's take this path right here, and let's go back right to this path. This is cyclic, right, process. Okay, perfect. Perfect. Now this is point A and point B. This is path 1 and path 2. Correct? Imagine we are in this way. Correct? So what should be then the work done? The work done is going to be the area under the curve. Now this is the area under the curve, right? This is work. Correct? That's the work done in this case. But let's see what happens when we apply the internal energy condition, means the first law of thermodynamics. What do we have? Changing internal energy. What should be the changing internal energy when you start and end at the same point, at the same state in this case? Well, the changing internal energy is zero, correct? Is zero. Wait, and then what should be our work? Well, remember from the physics of thermodynamics, changing internal energy equals to heat minus work. In this case, this is zero. What do we have? That work is just the heat added, correct? So we have again a sample right here. We put some heat. All the heat is converted into work. There's no heat used to change the temperature. We change the temperature every time we change temperature, right? We have a change in internal energy. If the temperature is constant, so internal energy, change in energy is zero, and all the heat is used to do work, all the work done. Got it? Okay, perfect. This is the case when we have a cyclic process. Now let's see finally in this part, let's go to the thermodynamic processes. We have 4 in thermodynamics, correct? And those are related to the state variables, right? When we have constant pressure, when we have constant volume, when we have constant temperature, and when heat is equals to 0. Okay, let's do it. So when heat is equals to 0, right, we call this adiabatic process. Adiabatic, it's a process, right? Process. We call this adiabatic. When temperature is constant, let's say T constant, okay, constant. When T is constant, we call this process isothermal process. Isothermal. Okay. When pressure is constant, we call this isobaric process. Isobaric. When what else? Volume is constant, we call this isochoric or isovolumetric. Isochoric or isovolumetric. Okay, we have one more. We have no, that's it. That's all right. We have these quantities. What about when internal energy is 0? The changing internal energy is equals to 0 means what? That the temperature is constant. Well, we go back again to the isothermal right here. Remember, we use this in the Bohr's law, right? T constant when we're dealing with ideal gases. Correct? Perfect. So these are going to be then the most important processes in thermodynamics: the adiabatic, right? Isothermal, isobaric, right? Isochoric, or isovolumetric processes. Right. So in the next, in the second part for this chapter, we are going back to these processes and find formulas. Right. All of them have formulas related now with the first law of thermodynamics. Let's use this first law to find new formulas. We already found some formulas, correct, using T constant, okay, which is, we just did it at the Bohr's law. When P is constant, again, using ideal gases. Okay, when P is constant is for Charles' law, for when B is constant is for Gay-Lussac's law. We did this in the previous chapter. But now let's go back to this analysis using, right, or involving the first law of thermodynamics, right, and we represent all of this in the PV diagram. Let's do it. Okay, this is point 1, point 2, for example. We have the isothermal, correct? We have the isobaric, we have what the isochoric, and we have the adiabatic process, right? Later in the next second part, the next video, let's go back again to these processes in thermodynamics. Okay, see you in the next video, part 2 for the first law of thermodynamics, chapter 19. See you later. Bye.